Yeah, 2014.
Yeah. Now he's going to try to convince us that you can actually do cosmology with clustering.
All right, yeah, more or less. I'll convince you that you have to do both cosmology and gastrophysics at the same time. All right, so yeah, it's nice to be up here visiting. I'm going to talk about work I've been doing with the Planck data since it came out, and then also a bit at the end with some data from ACT, the Atacama Cosmology Telescope, looking at constraints on the amplitude of fluctuations and the physics of intracluster gas. This is work, some with the ACT collaboration, mostly with David, and then some with Enrico Pyer, Blake Sherwin, and Kendrick Smith. Okay, so let me just start with this figure from the Planck SZ cluster cosmology paper. So this is a two-dimensional parameter space, sigma 8, which is the amplitude of fluctuations, and omega matter. The takeaway here is that the SZ clusters give you a much lower value in this parameter space of the amplitude of fluctuations and the matter density than what is inferred from the primordial CMB analysis. So the red contours are the Planck primordial CMB results, or at least they were the results that the people who wrote this paper thought were correct. So there's actually an error in that plot. This is the correct version of this plot. Nick, Battaglia, and Amir have also remade this and checked it. So the SE cluster contours are correct in that figure, but the CMB contours, they just literally plotted the wrong Markov chain. If you plot the right one, this is what it looks like. So omega matter from the CMB is just a bit above 0.3, and sigma 8 is something up close to 0.83 or 0.84. And you get much lower values from the SZ clusters results.
These are the 1 and 2 sigma contours?
Yeah, that's right. The 1 and 2 sigma. So the contours do overlap at the 2 sigma level, but the best fit values are pretty discrepant. And if you plot it in the 1D space, where this is the best constrained degenerate combination of these two parameters from the cluster side, then it's actually just visible by eye. This is a several sigma discrepancy between the cluster result and the CMB result. So what's going on here? I think that there's a few interesting possibilities. So on the SZ side, perhaps we just don't understand the gas physics of clusters. I think that's a likely possibility. On the CMB side, potentially there are subtleties in the CMB analysis due to things like foregrounds. David has been working on a reanalysis of the Planck data with some other postdocs in Princeton, and they have found some small shifts down. But I'm not going to talk about that today. I think that paper will be out probably in the next month or so from them. All right, and then the final possibility is that there's new physics at play. So, for example, massive neutrinos would lead to essentially this effect that's seen here. Basically, the amplitude of fluctuations inferred at low redshift from something like an SZ cluster count survey would be lower than what you would have inferred based on measurements at redshift 1100. So if you take these results at face value, that would imply that some of the neutrino masses is well above the minimum of 0.05 EV that's allowed by oscillation experiments. So I'm going to focus mostly on, almost entirely on issue 1 here, so as to figure out whether or not we can infer with confidence something about fundamental physics.
Because the massive neutrinos reduce the mass of clusters?
No, it's what the neutrinos do is that they have large thermal velocities in the early universe, so they can free stream out of potential wells. What this essentially does is just suppresses the linear theory matter power spectrum below their free streaming scale. And then once you compute the mass function with that suppressed matter power spectrum, you get fewer clusters at late times. That's how it manifests in this observable. But basically, the neutrinos just suppress the matter power spectrum below their free streaming scale. All right, so first I'll review quickly the SZ effect. Then I'm going to talk first about the TSZ power spectrum with respect to Planck mostly, and then a new measurement that I've recently done of the cross power spectrum of the thermal SZ effect with the CMB Lensing field measured by Planck. And then at the end, I'm going to talk about some real space statistics, including the PDF of the SZ effect with ACT data. All right, so a quick review. So the SZ effect is what happens when you have a CMB photon traveling to us from the surface of last scattering. It interacts, it inverse Compton scatters off of some hot electrons in the intracluster medium of a galaxy cluster. And this distorts the CMB spectrum in the direction of that cluster. You get a temperature decrement below this characteristic frequency of 218 gigahertz, a temperature increment above that frequency. There's really there's really two components. There's the thermal SZ, which is just due to the thermal motion of the ICM electrons. They're at a high temperature in this plasma. And then there's also a kinetic or kinematic SZ component, which is due to the bulk velocity of the electrons. But I'm not going to talk about KSZ today. This talk is only about thermal SZ. All right, so some numbers to keep in mind. At this typical observation frequency of about 150 gigahertz, massive clusters can produce temperature decrements of order hundreds of microkelvin. So these are larger than typical CMB fluctuations, which is why you can do a blind survey of the CMB sky like ACT or SPT and then find clusters. It's a nice signal because it's basically redshift independent because it's a scattering process rather than an emission process. So the signal doesn't decline with redshift. It's useful for a number of reasons, but one of the reasons people got excited about this in the past was that the integrated signal probes the line of sight integral of the temperature-weighted mass, which is basically the total thermal energy of the cluster, which correlates strongly with its mass. So the TSZ signal is a good tracer of mass. And then observationally, you can find the TSZ, or I guess KSZ, once you start resolving clusters, which are roughly arc-minute-sized objects in the CMB. All right, so a quick description of this unique spectral signature, which will come up again later in the talk, just to emphasize what this looks like. So this plot is the intensity of the CMB against frequency. So you have this initial black body spectrum and the dashed curve. Then if you let it pass through this hot gas in the ICM, the spectrum gets distorted. So below 218 gigahertz, you have a decrement in the temperature intensity. Above 218 gigahertz, you have an increment, and then there's a null frequency at 218. And this is the same information just as delta intensity. So the TSZ spectral function is this solid curve here. So you have a decrement at these lower frequencies, the null at 218, and increment at higher frequencies. So the Planck channels span this whole range, and then ACT has channels at 150 gigahertz and 220. In principle, there was one at 277 gigahertz, but there hasn't really been any science data from that channel. This is just a nice, picture of some simulated Planck data, which shows what a cluster looks like in the Planck bands. So you can see there's a decrement at these lower frequencies, the null at 217, and then an increment at the higher frequencies. And later in the talk, I'll show what a real cluster looks like in the Planck data, which looks about the same. All right, so how do you model this effect? So imagine we have some cluster on the sky with mass m and redshift z. If we want to know what the thermal SZ temperature shift at some position theta with respect to the center of the cluster is, the fractional change with respect to the CMB temperature is just given by the product of the TSZ spectral function, which is the curve that I showed on the previous slide, and then this parameter called Compton-y. So this encodes the product of the typical number of scatterings that occur as the CMB photon passes through the cluster times the average fractional energy change each one of those scatterings produces. So you have a line of sight integral of the number density times kT, so nkt, which is pressure. So what you're doing is you're taking a line of sight integral of the electron pressure profile through the cluster. So that's where the so-called gastrophysics of the ICM comes in. Basically, you have to understand what the pressure is of the ICM gas as a function of mass and redshift in order to compute this signal. All right, so then once you have some prescription for the gas, how would you do cosmology with TSZ or with Compton-y? So the traditional method is to basically find and count galaxy clusters as a function of their mass and redshift. So as I said, the TSZ signal can potentially give you a handle on the mass. To get the redshifts, you have to do optical or IR follow-up. And then you do cosmology by just directly reconstructing the halo mass function, which is sensitive to a number of cosmological parameters, in particular sigma 8 and omega matter. So the difficulties here are obtaining sufficiently accurate masses. This is a huge field of study, really. And then also understanding the selection function of your survey. Are the clusters that you're observing actually a fair sample of the clusters that exist in the universe? This is just an example of this kind of procedure, some work that we did following up ACT-detected clusters with the Sunyaev-Zel'dovich array, which is a much higher resolution instrument. This is a cluster redshift 0.8, which is quite massive. But it's a very expensive procedure to do this. This required many hours of SDA time just to get, I think we have 3 masses in this paper. All right, so I'm going to spend the rest of the talk talking about a different approach where instead of resolving and detecting individual clusters, we're just going to take a statistical approach to the TSZ signal. So in this case, we want to compute something like the power spectrum of the TSZ effect or bispectrum, or other statistical quantities. So we're working at the map level. There won't really be any more pictures of clusters in the rest of the talk. So here the idea is to get the amplitude of the fluctuations due to the TSZ signal as a function of angular scale. That's how you could just describe the power spectrum. And then you do cosmology by comparing this measurement to halo model calculations or full numerical simulations of cosmological volumes. So this is a measurement that came out earlier this year from the Planck collaboration. They combined their channel maps using internal linear combination techniques to make a TSZ map, and then computed its power spectrum, corrected for foregrounds, and this is what they measured. And this is the very first measurement of the TSZ power spectrum over all these angular scales, so sort of from degree scales all the way up almost to the arc-minute angular scales. And I'll talk more about this later in the talk. So the difficulties with these kind of approaches, on the theory side, you have to understand the ICM electron pressure profile as a function of mass and redshift. And then observationally, you have to be able to separate the TSZ signal from everything else that's in the CMB sky. So the CMB itself, point sources, the cosmic infrared background, the kinetic SZ effect. There's many things. All right, so why would you adopt this kind of a statistical approach? I think that there's a number of reasons that's advantageous. So one of them is that there are no selection effect related systematics. So there's no Malmquist or Eddington biases. We're never actually selecting individual clusters to study in this approach. There's no aperture within which you're measuring the mass. So people talk about masses measured within R200 or R500, basically enclosing some overdensity with respect to the cosmic mean or critical density. But in this case, like I said, we're never selecting a cluster or measuring its mass. You don't have to apply some sort of average or universal pressure profile to individual clusters to constrain them, because like I said, we're never selecting individual clusters. Instead, you can just self-consistently compute theoretically this statistical signal over the sky, where I think it's more sensible to use a kind of average profile over a population of objects. On a positive note, this is a very sensitive signal to this parameter sigma 8, the RMS amplitude of fluctuations on scales of 8 megaparsecs at redshift 0. This is just the amplitude of fluctuations in the universe with this particular way of describing it.
Roughly how that scaling arises.
Yeah, why does it scale so steeply? Yeah, the reason that happens is that, well, I'll talk about this in just a second, actually. I'll answer that in just a second. Yeah, so the TSZ power spectrum scales something like sigma 8 to the 7th. Higher moments of the TSZ signal, like the skewness, we pointed out last year, scale with even higher powers of sigma 8. And if you went to the kurtosis or the 5-point function, it scales increasingly steeply with sigma 8. But you pay a price with sample variance. I'll talk about that in a second. So there are these interesting non-Gaussian statistics to calculate. This signal, the TSZ signal, is not just characterized by its power spectrum. It's not a Gaussian random field by any means. It's coming from galaxy clusters, which are very rare objects on the sky. All right. So I think I've said these things. Theoretically, we need to understand the pressure profile, so the ICM Gastrophysics. Observationally, we have to separate out the TSZ signal. And then why measure Compton-y? Well, we're going to learn sigma 8, potentially omega matter, and then the gastrophysics of the ICM. All right, so let me talk first about the TSZ power spectrum. All right, so how do you compute this? So we have some prescription for the ICM gas that tells us the pressure profile. We do the line of sight integral to get a Compton-y profile, Fourier transform it to go to multipole space. And then all you do is sum up the contributions from all the clusters in the universe. Just add them up. So this involves doing an integral over the halo mass function, which is the number density of halos as a function of mass and redshift, and then the volume element. And this is where all the cosmological dependence comes in. So to answer your question, the reason that it's so sensitive to sigma 8 is because of this integral over the halo mass function, which is multiplied by this weighting. So this is going like Compton-y squared for the power spectrum. The Compton-y signal is heavily dominated by the most massive halos in the universe, which are very rare. So you have this exponential cutoff in the mass function, and then you're basically upweighting the exponentially sensitive part of it in the high mass tail, such that small changes in sigma 8 produce a very large change in the predicted signal. So that's why the scaling is so steep. And then the reason that the higher point statistics scale even more steeply is that if you put a higher power in here, you're just upweighting that high mass exponential tail even more, which makes it even more sensitive to sigma 8.
Okay.
Well, you could do an initial calculation of this just with virial type temperatures for the halos, and you would get a similar result. Okay. All right, so this is the so-called one halo term. Then there's also a two halo term, which comes from the clustering of clusters, but that's highly subdominant, but it is computed in all the results that I'll show.
Does the term ever dominate at low L?
It does below L of roughly like 5 or 6.
5 or 6?
Yeah. If you don't mask any nearby massive clusters. If you mask like Coma, a few other massive nearby clusters, you could suppress the one halo term at the low L's.
That's a really large scale. That's a dominator.
Yeah, it's kind of amazing.
CMB must be much bigger than the two halo term of that.
Oh, absolutely, yeah.
By what order of magnitude?
Yeah, you have to use frequency space methods to separate the TSZ signal, in this case from the primordial CMB, for example.
But
Yeah.
do you have a sense of how much bigger the primary CMB would be compared to the two halo term?
Oh, it's certainly orders of magnitude bigger. Yeah. All right. Yeah, so I'll talk about how that's done in a little bit. Like I said, you rely on the frequency space characteristics of the DSZ effect in order to separate it out from the other components in the CMB sky. All right, so let me just briefly discuss how we model the astrophysics of the ICM, at least for these calculations. So to lowest order, the ICM is hydrostatic equilibrium between gas pressure and the dark matter gravitational potential. You can assume gas traces dark matter, a polytropic equation of state. This is what people were doing 10 and 15 years ago. This is in Komatsu and Seljuk. So we have the hydrostatic equilibrium equation shown here. When you do this procedure, you obtain this overcooling problem in the center of the cluster where you form many, many stars, which is in severe disagreement with observations. And then also the pressure profile doesn't converge at the edge of the cluster, so that's a problem. There's a lot of additional physics that are needed. So there are virial shocks that have to be accounted for at the boundary outer regions of the cluster. You also have feedback from supernovae. There's star formation. You might have some cosmic ray pressure support. There are things like magnetic fields and plasma instabilities, which are certainly not being modeled in cosmological volume simulations. And then two things that have been found to be particularly important in recent years. So in the outer regions of clusters, you can have turbulent pressure support, which gives you this non-thermal term on the left-hand side of this equation. So what that lets you do is add another term on the left-hand side, so then you can suppress this thermal term, and then that therefore suppresses the TSZ signal. And then the other thing that's been found to be pretty important in recent times is AGN feedback. So in this case, the feedback that the feedback that the AGN puts back into the intracluster medium can heat the gas up, which can expel it from the cluster or just push it out into the outer regions of the cluster and kind of flatten the pressure profile by depositing hot gas in the outer regions.
The AGN can actually expel gas from the cluster.
For the lower mass,
How low do you have to go in mass for it to actually unbind something?
I think by the time you get down to, say, like 10 to the 14, like 5 times 10 to the 13.
So below the cluster.
Yeah.
Well, but even at 10 to 14 observation, you don't find all the variants.
That's right.
No, but I don't think it's the AGN that's expelling it.
I'm saying they're not all the variants.
Sure.
Subject suppressed.
Yeah. All right. So the model that I've adopted throughout all the work that's going to be shown is a result from simulations done by Nick Battaglia, who I think was here. And these are Gadget SPH simulations of large cosmological volumes. And the new twist they had is that they have a subgrid prescription for AGN feedback, which is not. This model is not tuned to match really any observations. It's tuned to match high-resolution simulations of clusters. But they put this prescription in and then ran many boxes. And this stacked profile that they've pulled out has been found to actually agree with real data over the last few years, I think, better than essentially anyone else's profile. So I think it's a nice thing to use. So you basically have this generalized NFW form for the dimensionless pressure profile. Then there are many parameters here which are provided in the fit. And then additionally, some of the parameters also have mass and redshift dependencies as well, which capture deviations from self-similarity. And as I said, this has been compared to many different observations in recent years, and it agrees quite well. So this is a stacked pressure profile of the most massive clusters in the universe done by Planck, and the Battaglia model is shown in brown on this plot. So it's in very good agreement over most of the range, and the outer regions might be slightly high, but the authors of this said that it was the best fitting model that they had. All right, so given a model for the gastrophysics, and then we use standard Tinker prescriptions for the halo mass function and bias, you can then compute the TSE power spectrum. So I wrote a paper earlier this year with Enrico Peyer, prior to the Planck data release, saying, given what we know in modern times about gastrophysics and cosmology, what can we actually hope to learn from the TSE power spectrum? Can we actually learn anything about cosmology? So we did a very detailed forecasting paper, and we let all the lambda CDM parameters vary, as well as allowing primordial non-Gaussianity or neutrino masses, one or the other, to see if we could constrain these extensions to the standard model. And additionally, we let some free parameters float to describe the gastrophysics, so some of the parameters in the model that I just showed. So just to quickly summarize this paper, we didn't find that it was going to be possible to really constrain primordial non-Gaussianity with the TSE power spectrum. But neutrino masses, the constraints are potentially hopeful. So this shows what happens to the TSE power spectrum as you add some massive neutrinos in the universe. Essentially, you just change the amplitude of the spectrum by a small amount. And also to discuss the 2 halo versus 1 halo comparison, you can see this is the 2 halo term and this is the 1 halo term. So 2 halo is only really relevant at incredibly low L's, say below L of 5. All right, so the punchline of our...
Sort of nominal model on that one? Is it one with solid lines or one with dashed lines?
The nominal model is the black solid line. Yeah, it's a WMAP9 cosmology with the battalion pressure profile.
So then it looks like the 2 halo term. Oh, the dashed lines.
Sorry, the total is solid and then dashed and dotted are 1 and 2 halo. Yeah.
So here, you showed that the average pressure profile matched up well with the stacked ones
Mm-hmm.
from the battalion et al. But in fact, the actual observation is each one has its own profile. So
Right, so that's why they stack them to get an average.
But for this, the difference between those curves there, how do you know that the difference, if you didn't assume a spherically average profile, you would get the right answer?
Right, so in Nick's original paper where they derived the profile, they compared this fitting function result to the direct direct line of sight integration of their cosmological boxes. And on largish angular scales, certainly below L of 1,000, the deviations from things like spherical symmetry or scatter about the mean profile don't contribute very much. Certainly less than 10%, probably order 5% or something. Yeah. Yeah, I imagine that would have a similar effect. I mean, it's like adding a warm dark matter component, right? So it will also suppress the matter power spectrum in a similar way. Yeah. All right, so the punchline of our paper was essentially that you can't just fix your gastrophysics model and constrain cosmology. You really have to do both of these things simultaneously. Otherwise, you're going to bias your cosmological results, or more importantly, underestimate the errors on your derived results. So we computed the forecasted possible constraints on the neutrino masses as a function of the fractional prior on your knowledge of the gastrophysics. So without going into all the details here, this is just the fractional prior on the different parameters in that gastrophysics model, which we let decrease simultaneously. So at 0 here, you'd be saying we know the gastrophysics model perfectly. And the Planck constraints that we forecasted are in red. These are for different masking scenarios, but don't worry about that too much. So the punchline is that if you could say you know your gastrophysics model quite well, then the forecasted constraint, just from the TSE power spectrum, is actually fairly competitive with other probes in the range of 0.1 to 0.2 electron volts. So we predicted that Planck would be able to measure the TSE power spectrum around L of 100 to 1,000. And indeed, a few days later, they put out their paper, and that was what they measured. So we were excited to see this. So this is the Planck TSE power spectrum I showed earlier. So what they do here is they take their channel maps, and they use ILC techniques to combine them using the frequency shape spectral function of the TSE effect in such a way that TSE is preserved and other components in the map are minimized. Then they compute the power spectrum of that map. Then they subtract off estimates for residual power in the map from other things. And these are the final points that they get. So one dismaying thing about their analysis is that they just fixed the gastrophysics model to this so-called Arnaud universal pressure profile model, and they didn't consider any variations in it. I don't know exactly why they did that. But in that context, they constrained this degenerate combination of sigmate and omega matter to quite high precision. And really, this is just limited by the uncertainties in the residual foregrounds in this spectrum. The statistical error bars are much smaller than what's shown here. These are basically just due to uncertainties in how much power is being contributed by things like galactic dust, the cosmic infrared background, and point sources. But the puzzling thing here is why this value comes out so low compared to what you get from the primordial CMB. So this is the same quantity computed with the Planck and WMAP polarization CMB analysis. And as you can see, these disagree at many sigma. So you plot this directly at the power spectrum, at the TSZ power spectrum level. This is what it looks like. The Planck measurements are in the black crosses. And then if you just take the Planck primordial CMB cosmological parameters and predict what you should have measured for the TSZ power spectrum, you get this gray band, which lies completely above all the measurements. So this is essentially what I was starting to talk with. What's the origin of this discrepancy? So I'm going to talk now about some work that I've done since the Planck data.
Gray band was using the Monique's pressure profile? Or?
No, these are all using the Battaglia pressure profile. Yeah, this is done by Nick, just to.
Battaglia one doesn't fix it either.
No, not exactly. No, you get essentially the same results if you use Nick's profile or if you use the Arnaud pressure profile. Yeah, it's the main thing that I would say is uncertain about this result for me is the fact that they have to subtract off estimates for how much residual power is coming in from the foregrounds. And if you look in their paper, the initial measurements of all these points lie somewhere. I would say these aren't affected too much, so they're like here, but then the ones up here actually look like this or something. So the initial measurements look like that, and then they subtract off this estimate for residual power. And if they over-subtracted just by 10 or 20%, you could have biased sigma 8 by, well, 10 or 20% divided by 7, so a few percent, and that would go a long ways towards resolving the problem.
To harp on this a little bit longer, but what is the difference you see in this between the Battaglia and the Arnaud pressure profiles?
You mean in the predicted TSZ power spectrum?
I don't know what all the
No, that's not here. It's in the Planck paper. I used to have that figure in this talk, but I took it out.
What sort of range?
Yeah, you mean if you fix the cosmology and just use those two gas physics models, like how much different does it look? They look pretty similar at this level. Yeah. Well, they look pretty similar up to the choice of the so-called hydrostatic mass bias, which is this free parameter that you can basically rescale the Arnaud results by at your choosing. And Nick's model corresponds to something like a 20 or 25% value for this hydrostatic mass bias parameter. Once you fix that, then Arnaud and Battaglia look pretty much the same. Okay, so I'm going to talk about some work of my own with the Planck data since it came out, attempting to measure the cross-correlation of the thermal SZ signal with the CMB Lensing signal measured by Planck. So let me just quickly review what CMB Lensing is, so we're all on the same page. So as CMB photons travel to us from the surface of last scattering, they get deflected by a large-scale structure along the line of sight. And essentially, this is just a remapping of the CMB. So you have the initial unlensed CMB, which gets remapped by this deflection field D to give us the observed lensed CMB. And these are basically coherent. There's small shifts of the CMB fluctuations that are coherent across degree scales. So this shows simulated CMB data where you have an unlensed patch. And here's what it looks like when it's lensed. So you can see there are just degree scale blobs that get shifted by a few arc minutes. And using the way that the small scale statistics of the CMB are changed by gravitational lensing, you can reconstruct a map of this deflection field D, or the lensing convergence or lensing potential. They're all really equivalent things. So this is an example using this simulated ACT patch of a reconstruction of the deflection field. All right, so how do you compute, theoretically, this signal that we're looking for? It's very similar to how we computed the TSZ autopower spectrum, except that now we also need to know something about the lensing side of things. So given a model for the density profile of each halo, say NFW, you can compute its contribution to the lensing potential. And then you just have a one halo term and a two halo term. So one halo, you're correlating the gas and the matter in the same halo with each other. And then the two halo term, you're correlating the gas or Compton-y in one halo with the matter or lensing potential from a different halo. So the one halo term dominates on very small scales, and the two halo term dominates on very large scales. So this is what the signal looks like for our fiducial WMAP9 cosmology with the Battaglia pressure profile. So the 2 halo term is in red here, which dominates at these larger angular scales, and the 1 halo term is in blue, which dominates at the smaller scales. The total is the solid green, and then the dashed and dotted curves show what happened if you change sigma 8 or omega matter by a small amount. Over the range where we're going to measure the signal, it scales roughly like sigma 8 to the 6th or omega matter to the 1.5. So this is another way of assessing how correlated the two fields are. You can make a dimensionless normalized measurement or measure of their cross correlation, and over up to about L of 1,000, there's something like 30 to 40% correlated, and then above that, at very small angular scales, the correlation increases because basically the same gas, the same cluster's gas and matter is being correlated. In this case, the 1 halo term just takes over. All right, so what masses and redshifts are contributing to this signal? This plot shows the cumulative contributions to the power at L of 1,000 for these 3 different spectra. So the TSE autopower spectrum is red, the cross is in black, and the CMB Lensing autopower spectrum is in blue. So the CMB Lensing autopower spectrum is sourced by halos down to very, very small mass scales. The TSE autopower spectrum comes from clusters, so things above 10 to the 14 solar masses. And then this cross-power spectrum essentially lies in between the two. So you have most of the signal coming from objects between, say, 10 to the 13 and 10 to the 14.5 solar masses. It's kind of interesting because these are quite low mass objects, and in particular, they're significantly lower than what the TSE autopower spectrum probes. And this is an observable that people have often said is quite sensitive, and even dominated by objects that are so low mass that we haven't observed them. And this is a signal that's dominated by even lower mass and higher redshift objects. So these plots show the redshift kernels of these different signals. So the CMB Lensing autopower spectrum has a kernel that goes out to very, very high redshifts. This is redshift 3, goes way beyond that. The TSE autopower spectrum mostly sourced below redshift 1, but does get quite a bit of signal out from 0.5 to 1. And then this cross spectrum, when you basically take something between these, you have contributions from, say, redshift 0.5 to 1.5. So it's quite high redshift and low mass, which is what makes it, I think, gastrophysically interesting. These are objects they haven't observed with X-rays or other techniques.
So you're basically probing groups at redshift of 1.
Yeah, exactly.
Which we know nothing about.
Yeah, so I think it's cool. Yeah, it'll also be interesting whether or not, well, I guess we'll see, whether the models actually work in that regime. All right, so how do you measure this? It's really this easy in principle. You have a Compton-y map and a CMB Lensing potential map, and you cross-correlate them. So this map, the CMB Lensing potential map, was released by the Planck collaboration. It's a nice data product. It's great to work with. They did not release a Compton-y map. As to why they didn't do this, I don't know. But step 1 of this procedure becomes make a Compton-y map. So this summer I wrote an ILC pipeline to combine data from the different Planck channels to produce a reconstruction of the TSE or Compton-y signal. I'm happy to tell you about how I did that, but let me not go into the details here. This is the result. So I couldn't resist titling this map the do-it-yourself map, DIY Compton-y, because they didn't release their own version of the map. So this is the so-called DIY map that David and I have made. So we've masked out the galaxy quite heavily here. The dust emission from the galaxy can really bias the reconstruction. This is around 25% of the sky that's shown here. And we've also masked out point sources, as well as, and mostly just the galaxy. Yeah, so these rings, actually, it's funny because they are exactly where that is, but actually what this masking is that in the individual, so we're using the Survey 1 and Survey 2 data from Planck, and each of those individual surveys doesn't quite cover the full sky. So Survey 1, I think, leaves out this little region, and Survey 2 leaves out this region. But it does actually look like it's just the solar system. So, yeah. All right, so here's a cluster in the map. This is Coma, which is a massive nearby cluster. And on the left, you can see the individual channel maps. So there's decrements at low frequencies, the null, and then increments at higher frequencies. And this is the reconstructed Compton-y signal with some point sources masked out in this field. It's kind of fun to see what the lensing potential map looks like at that location. It's just mostly noise by eye. But I should say the lensing kernel is not really optimized to pick up such a nearby object as Coma. Anyways, we cross-correlate the two maps. This is the histogram of the Compton-y map, but this is just evidence that there is a lot of TSE signal here. We cross-correlate the two maps, and this is what we get. So it's an 8.7 sigma detection at first sight, and our fiducial model is shown here in green with the 2 halo and 1 halo terms. So then you ask, is this a real signal? We've done many, many null tests to check it, and the main contaminant that has to be worried about here is the cosmic infrared background, the CIB. So this is a signal that's sourced by dusty star-forming galaxies at redshifts of 2 and 3. It correlates very strongly with the CMB Lensing field because their redshift and mass kernels are very well matched, something like an 80% correlation. There's an entire Planck paper which is about this, and this is a result from that Planck paper. So they've stacked on hot spots and cold spots in the CIB, and indeed a hot spot where stars are forming is an overdensity in the matter field and vice versa for a cold spot, and this is just a noise map. So we have a procedure for assessing the leakage of the CIB into our Y map and then removing how much of that has contaminated the lensing cross-correlation. And this is what you get after you do that correction. That's the blue squares that are shown here, and it becomes a 6.2 sigma detection. We've done that correction in 2 different ways and get consistent results in both ways, so it seems to be a robust signal. This is the first detection of this cross-power spectrum. So,
Do you detect the autocorrelation of the TSE?
yeah,
Probably not very well.
it's much harder. The requirements on the foreground removal are order of magnitude more stringent in order to I can show you that after the talk,
So can you
but it's much harder to do
give
that.
me a sense of what I should understand from these trends here?
Well, there's a lot of noise, I guess. I mean, the points are clearly scattering. I'll show a rebin version of the measurement in a second. And I'll just go ahead and do that. So what can we learn from the measurement? So first, let's look at gastrophysics. So fix the background cosmology to WMAP9, and then compute the signal for a bunch of different gastrophysics models. So our fiducial model is the green curve shown here. Then I've plotted a few other things. So the purple dashed dotted curve is an adiabatic cluster model, also from Nick Battaglia, but this has no cooling prescriptions and also no feedback prescriptions of any kind. It's purely adiabatic. So you get a lot more Compton-y for a given halo mass in that model. And then the other 3 curves I've shown here are 3 different variants on the R node universal pressure profile with different levels of this so-called hydrostatic mass bias. So the Planck team's claim was that in order to reconcile these sigma 8 omega matter discrepancy I showed at the beginning of the talk, you needed to have a bias of something like 45% in the SZ measurements in order to let the sigma 8 value float back up. Our results are in, I would say, tension with that claim. So there's roughly a disfavored, that model is roughly disfavored about delta chi-squared of 10 by our measurements. So these are just rebinned points of the spectrum that I showed a minute ago. And it turned out that the fiducial model we started with is the best fitting result here, although I did the theory calculations months before we ever measured anything. So that was kind of exciting to see that happen. And this is testing these gas physics models in a mass and redshift regime where they weren't calibrated and where we don't have other constraints. So I think it's interesting for many reasons. All right, we can also constrain cosmology from these results. So if you fix the gas physics model to our fiducial Battaglia model, you can let sigma 8 and omega matter float. This just shows the same results I had earlier in the talk. The SD clusters from Planck are in cyan. The Planck CMB is green. This is WMAP9. The TSE power spectrum constraint comes in low, just like the SE clusters constraint from Planck. This is my own reanalysis with the Battaglia model of that data. And then our result for the cross-power spectrum gives you this contour, and then the pink or purple contour in the back is from Amir and Nick's recent paper where they cross-correlated a TSE map with a Rosat X-ray map. So plotted in 1D space, this degenerate combination of the 2 parameters looks like this. Our recent cross-spectrum measurement is consistent with WMAP9 and this TSE cross X-ray result. And the Planck CMB is marginally consistent here as well. It seems that most of the tension is coming from these official Planck results down here. So we measure this combination at pretty high precision, about 0.83 plus or minus 0.03. And then there's one final interesting thing that you can do here, which is to ask the question, what if I let not only these cosmological parameters float, but also imagine starting to free one of the parameters in the gas physics model? So as an initial step to doing that, I just let the overall mean amplitude of the pressure profile float. So this is the mean pressure of any cluster, essentially, in the universe.
I'm sorry, what is TSZ auto?
Oh, sorry, that's the TSZ auto power spectrum that I showed earlier. Yeah. So when you do this, you can begin to break this degeneracy between the cosmology and the gastrophysics. So this is a 2D plot where the x-axis is the degenerate combination of sigma 8 and omega matter. And then the y-axis is a normalized version of this mean amplitude of the ICM pressure. So because the cross spectrum here has one power of Compton-y, or one power of pressure, and the auto power spectrum has two powers of pressure, they actually depend differently on this parameter. So you can break the degeneracy, basically.
So I should think of this as the total non-thermal pressure component averaged over all the radii in the cluster.
Yeah, and over, I guess, all
And over all
cluster.
redshifts.
Yeah, everything. Yeah, it's just this overall amplitude. Yeah.
And the stacking that you showed earlier would work for any of these values. You said the Battaglia was the best fit so far to the stacking.
Oh, yeah, so that's a stacking analysis just done on like the 50 or 60 most massive clusters in the Planck sky. Yeah, and that's done for the fiducial value, so 1.0.
But if you, that's
Yeah.
what I'm asking. So if you
Yeah.
changed it to 0.8, you'd be able to mess around with some.
It would disagree with those measurements. Yeah, I mean, that pressure profile is for these massive clusters is measured fairly well.
And the mass is measured well enough.
Right. So then it comes down to the mass measurements.
Yeah.
So it's a different approach. Yeah, there's a reason I haven't put those results on here because it's a little bit tricky to attempt to fit them into the same framework given how we have right now. Exactly. Yeah. So this result is basically meant to be a demonstration of this possible idea. At 2 sigma, the combined constraint is consistent with a very standard value of sigma 8 and its standard value of the pressure. But when you combine them, you actually get pushed to these high values of sigma 8 and low values of P naught. But that really just comes from the fact that this TSZ auto power spectrum is so much lower, which comes back to this foreground subtraction issue that I think requires much more investigation. So just to wrap this up, this is a direct confirmation that the hot ionized gas traced by TSZ is correlated with dark matter over a wide range of scales in the universe. So I think it's a nice thing to have confirmed about the universe. So in the last few minutes, let me just highlight some interesting work that's in progress right now with ACT on a different approach to some of these issues. So now we're going to switch to real space and look at the 1-point PDF of the ACT TSZ signal. So this is just a picture of ACT. I don't know who took this, Mike, but yeah, I haven't given them credit. ACT observed the sky at 150, 220, and 280 gigahertz. I'll just show data mostly from 148 here with a resolution of about 1 arc a minute. So this is work that we did a couple of years ago where we looked at the histogram of temperature values, so the PDF, in the ACT 148 gigahertz maps. So you have this large Gaussian noise component, and then at this frequency, the TSZ signal is negative, so you have this negative tail that comes from the TSZ decrements. And then in principle, there's also a point source tail here at positive temperatures, but we've removed those with a masking procedure, which I can tell you more about. So we did the simplest thing you could do with this histogram, which was to look at its skewness. It's clearly non-Gaussian by eye. And we measured the skewness at 5 sigma, and then I worked out the theoretical interpretation of this measurement where we constrained sigma 8 to a few percent using the fact that this signal is so extremely dependent on sigma 8. And once you start measuring these higher point statistics of the TSZ signal, there's interesting things that you could do. So the power spectrum depends on sigma 8 to the 7th, roughly. This is skewness signal, something like sigma 8 to the 11th. Once you know these scalings, which are pretty consistent, even if you change your gas physics model, you get very similar values for these, really driven by the cosmology. You can then combine these statistics to break this ICM cosmology degeneracy. So you can just cancel the sigma 8 dependence, for example. So that's what this plot shows. We defined a new statistic, the rescaled skewness, where you divide out this dependence, and then there's no dependence on sigma 8 anymore. So this is sigma 8 on the x-axis, and all these curves are just flat. But there is a residual dependence on the gas physics. So there's 4 models plotted here. These 2 models at the bottom are purely hydrostatic equilibrium, adiabatic type models. And then I have R node with a 15% hydrostatic mass bias and the Battaglia model here. And this is updated with SPT results that came out, I guess, last year now. of the TFZ bispectrum. And using those results, these adiabatic models are disfavored at roughly 2 sigma. Sorry? Oh, it's on here. It's the low. It's the red one. Yeah, it's the most intention. Yeah. No, sorry about that. Yeah. All right. So that was what we did, I guess, last year. That led to me starting to think about whether or not we're actually using all of the information in this PDF. So we just used the skewness for that measurement. But if, in principle, we could compute this whole PDF itself, perhaps there's more information in the additional moments of the distribution. So thinking hard about this and working with Kendrick Smith, we came up with a way of working this out. The basic idea is to rephrase the question as how much sky area is subtended by Compton-y or TSE values in some given range. So if you have a cluster Compton-y profile that looks like this, imagine some bin spanned by y min and y max. Those just correspond to circles in this model. In that case, all you're doing is asking for the area between the two circles. So you do that, and then you add up this area for all the clusters in the universe, and that gives you the noiseless calculation of the thermal Z PDF. But there are complications to this. So one obvious one is that if there are overlaps along the line of sight, this isn't going to work. So this only works if your experiment has noise levels such that you're only going to resolve clusters that are so rare that there aren't going to be any overlaps along the line of sight. This approximation is valid for ACT, but probably not for future experiments, so it will require some additional thinking. You also have to worry about non-TSE contributions in the CMB map, and one particularly hard thing is inhomogeneous noise in the map, which makes the covariance matrix difficult to calculate. But the idea here, I think, is quite useful to see how this works. So the PDF cosmologically is great because now you're using all the TSE moments. So the higher moment scale with very high powers of sigma 8, so it's very sensitive to cosmology. And then you can use basically a generalization of that rescaled skewness type idea to break the degeneracy between cosmology and the ICM gastrophysics. So the basic idea is that the gastrophysics models out in the tail of this PDF give pretty similar predictions because in this regime, the signal is coming from very massive clusters in the universe where gravitational processes mostly dominate the energy budget. So you can determine sigma 8 essentially from the tail of the PDF. And then as you go down to lower Compton-y values, you're getting signal from less massive, higher redshift objects for which the gas physics models disagree much more, which allow you to constrain the gastrophysics from that regime. So we've set about doing this with the ACT data. So the red points shown here are the same data set that I plotted here in this blue histogram. And then there's 2 theoretical calculations using the modeling I just showed on this plot as well for different values of sigma 8. And this is all preliminary, but they're hard at work on actually doing this. And it appears that it actually can work to do these things that I suggested. The error on sigma 8 decreases by something like a factor of 3 if we make the same analysis assumptions as we did in that skewness analysis. So we'll be getting down to percent level constraints on sigma 8. And then I think what's more cool is that it really does let you break this degeneracy between the gas physics and the cosmology. So just letting that overall pressure amplitude float again, in addition to sigma 8, you can constrain these two things simultaneously, the pressure to something like 10 or 20%, and sigma 8 almost still to the percent level at the same time. So we're at work right now with a big simulation pipeline in order to characterize the covariance matrix of these points. The bins are quite correlated because if you have a very massive cluster, it will source some signal way out in the tail, but then it will also have pixels in the outer regions of that cluster that give you signal down here, which leads to a non-trivial covariance matrix. But it is tractable, and this is in progress. So let me just wrap up. Hopefully I've convinced you that there's a lot of interesting things to be done with thermal Z measurements, both for cosmology and gastrophysics. And I think using these cross-correlations and higher order statistics, we can break degeneracies between the ICM and the cosmology and figure out what's going on with this discrepancy. Thanks.
Any questions?
Let me sort of rephrase the question I was trying to get at earlier. What if you fix the cosmology based on other measurements? How much do you think you can get out in trying to determine what the gastrophysics might tell you in terms of pressure profile, shape?
Yeah, I agree with you completely about that. I guess, so this plot maybe is the first thing I would use to answer this. I mean, so we are fixing the background cosmology or using primordial CMB data and then asking how much variation is there in the space of gastrophysics models. And, there's order factor of 4 changes here between the different models. In terms of isolating what's going on with the different populations at different redshifts, I mean, I think what we really need is a better parameterization on the gastrophysics side of, like, a minimal set of parameters that capture what's going on with some mass and redshift dependence probably, but such that you can vary those, like, 4 or 5 parameters or whatever in a Markov chain approach and simultaneously kind of fit those with the cosmology. And that's a direction I'm hoping to push forward in after this.
So these error versus you're showing they're 1 sigma?
In this plot, they're all 1 sigma, yeah. Mm-hmm.
So they're not really inconsistent.
No, I'd say that there's tension rather than inconsistency.
So how are you going to narrow these down? I mean, you sort of give an indication that one might be able to narrow things down using
Right, so the Planck CMB,
other distributions, but
yeah.
really to solve this.
Well, the Planck CMB contours will shrink as we get the rest of the Planck data, et cetera. Well, there's polarization data still coming in, as well as the full 5-season temperature data set. So those will shrink by some amount. On the TSE side, yeah, to get the errors to shrink, I mean, I just think that we need to push forward on these approaches where you're using multiple statistics simultaneously to get around the degeneracies of the gas physics and the cosmology. So that way, I mean, the error bars on these things are dominated by systematics, really, on the TSE side that come from the ICM. So it's just a matter of, I think, having a clever enough approach to break these degeneracies and get around that issue.